the speaker form as part of the assessment for the graduate students. So please make sure you complete one and send those into Josh after the talk. And if you've missed any from previous weeks, you can also fill them in and send them to Josh, and he will compile them in that student's folder so that we are ready for SACs when that time shall come. Also, a quick comment before we get started today with Maram. Next week's colloquium is one in which you must register in advance. It is a guest speaker that we are hosting with the Water Institute. So please make sure to go on. We will try and send multiple reminders throughout the week between now and then to remind you all. But go online and actually register for that meeting, or else you will not be able to log in. We will have a copy of it up and running in the lab too in here. For those who forget, they can just come to class. But if you're going to do it from home, you cannot log on and use the link we normally use. Instead, you need to have registered through that special link. Any other notices? Good. Okay.
Question.
Oh, we got a question.
Sorry, if we're planning on coming, like to watch it in here, do you want us to register anyway, just for registration numbers?
Sure.
Does it
Yeah,
matter?
that might be useful.
Okay.
Yeah, and just in case, because I think they're going to close registration at some point. We're not hosting it, the Water Institute is, so just to make sure that they see we have good representation. Okay, so we are going to get underway. So today, Maram is going to give her PhD presentation, and you can see here that she's looking at the role of floods and mining disturbances as drivers of fluvial instability. In the middle, Amite, I'm sure I mispronounced it, river in Louisiana. So Maram, why don't you take it away?
Okay, thank you, Professor Jane, and thank you everyone for attending my presentation, the role of flood and mining disturbance as a driver of fluvial instability in the middle Amite River, Louisiana. Special thank to my community member, Professor Mosa and Professor Fick and Professor Ash and Professor Preneur. I will start my presentation. Okay, to change. I will start my presentation by the outline. I will discuss the introduction, the study area, the research objective, the significance of the study, overview of the literature review, the dataset source, and the methodology, the result and discussion and conclusion, and lastly, the reference. So the introduction, so as we know, river dynamic system experience erosion, transport, and deposition. The imbalance of these can be caused by riverbed degradation. One reason for the river degradation, it's the mining or bit mining, which usually removes the surface material, which causes a many hydrological change in the environment. And the USA, Louisiana is one of the states that use the open pit mine to extract the sand and gravel. The open pit mining is easy operation, but the because of the easy operation can cause a lot of the surface eco-hydrological challenge in the environment, including the river instability, the surface and the groundwater level degradation, and the vegetation density and the flood habit degradation. And here a graphic adopted by the Kondo paper. It's generalized the environment change caused by the floodplain mining. So the Amite River is a start of the southwest Mississippi state and flow to the south for approximately 120 kilometers to Lake Murphy in Louisiana. Here, so the river drain is approximately more than 5,000 kilometers square, and the basin is divided to 9 sub-basins. The elevation in the Amite watershed is considered low elevation. The maximum elevation just 152 meters, and the lowest elevation is near the lake. The watershed, it's a very high populated area. It's approximately 500,000 people live in the basin, mostly concentrated in the water area. The river have been experienced a lot of hydromodification to reduce the flood risk in the populated area. Also because of the land use and land coverage change, the river has been mined since the 20s. And here image of the middle Amite River and the mining activity. It's been concentrated in the middle Amite River, which between the Santa Helene and East Filsham and Livingstone and East Butcherall Parsheet. And here the time series mining of the Amite River from 1987 to 2019. Two different bands, the RGP band or the true color, and the other one, it's a near-infrared band. The near-infrared band, I put it because it highlighted the wet bits or the water in the open bits. So my study area is extended from the state boundary between Mississippi and Louisiana until the Dunham Spring. There are 4 gauge stations in this study area. The gauge station Darlington, Greenville, and Magnolia and Dunham Spring. The mining activity basically is considered in this study area. The literature review, so there are considerable amount of the literature review have been published in the Amite River. It can be divided to 3 aspects: the bioenvironmental change and hydrological change of fluvial dynamic. There are less fluvial dynamic have been published in this area. Has been has been any detail about study about the land use and land cover change in the recent periods. Also, my dissertation will bring a given complex mining activity and how the hydrodynamic change in the Middle Amite River and understanding the historical and the flood plain variation. The research objective and the scopes. The first question is how did the 2016 flood change the bit size and the depression hierarchy in the floodplain, and how does the spatial variation of the mining number and the size associate with the intensity of the mining? I will use the level set method and the localized tree control. The second question is investigate the morphological river change after the 1980s, based on the last published work by Morphological, and how does the land cover and land use contribute for the channel instability, and how strong the correlation between the channel instability and the land use and land coverage. I use 3 morphological indices: the river network change index and lateral mobility index and channel mobility index. So the significance of the study is to bring understanding how the river has response to the flood and the mining activity in the term of the channel control. Also investigate how the land cover and land use make the floodplain more vulnerable to the flood events. And this investigation and understanding can give insightful for best practice for management for the floodplain. The data set I use it's a LiDAR data. It's 2000. I use LiDAR data and digital orthophoto quarter to quarter or DOQQ. The LiDAR data is 2014 and 2018, and the resolution is 3 meter and 1 meter. And I downloaded it from NOAA website, and the DOQQ, it's kind of time series of 1989 and 2004, 2010, and 2015, 2019. And the spatial resolution, it's 1 meter, and this was downloaded from Atlas, Louisiana Atlas. The first paper, I will discuss the topographic change associated with the 2016 catastrophic flood in the mining Amite River using the level set method. So in August 2016, a heavy rainfall caused a catastrophic flood in Louisiana, more than 31 inches or 778 millimeters just in 3 days. 12 parishes declare emergency and major federal disaster. The water flow in the Amite River caused the flood, and the gauge station there, it's hitting the record. The anthropogenetic hydrological caused a lot of alteration in the watershed, especially in the mining bush. And here, a graphic for the LiDAR of Louisiana for the flood event. And here, a table of the gauge station of my study area, the Middle Amite River. I will not spend so much time here. It's just the Darlington, the 4 gauge station, the Darlington and the Greenville, Magnolia and Dunham Spring. And here I just want to add the historical crest base, mainly it's because of the 2016 flood 2016. And here the aerial photography showed the erosion of how the landscape changed over the time from 2005 and 2017. So the question, how did the 2016 flood event impact the floodplain morphology? The hypothesis, so the position and the shape of the open pit and the channel morphology have been changed due to the 2016 flood. So the aim of this is to investigate the change of the channel and the per area of the Amite before and after the flood event. Also, to automate the process of the detection and extraction, the bit depression using the level set method and localized tree contour. Sorry. So the methodology, here the flow chart of the methodology. So basically two concepts, level set method or SM, a localized tree control, and the flow chart. So using the LiDAR D, it's go through the processing and identifying the seed contours and contour tree method, and identify the quasi-pore contour and the threshold and the depression hierarchy or depressions level. So the level set method or the LSM, it's proposed by Archer and Sitmian in 1988. It's basically to analyze the shape of geometry by the topography and the floor. So the basic of the level set method, it's how it detects the geometric based on the flood and the based in the water. So the XY here, it's the point, the coordinate, and the phi. So for example, this shape, each point located in this line, it's considered 0, where all the point inside this shape will be more than 0, and out this the shape which will be less than 0. So it's illustrate the level set method. And here, for example, this is the depression, and the water, and here is the flood or the water. So we can see when you use the level set method can be how the shape it changed based in the water level. So the level set method, it have been developed and have been used in many disciplines in image processing and computing of fluid dynamic. It have been used also in the medical to detect and analyze the image. It's used also in the environment study to detect the shoreline and the lake depressions. And here example of the have been used the level set method and the environment study. So the levels, so I use this concept to detect the bit depression. So using the LiDAR, using the DIM. So before the process, before using the levels, the DIMs, the DIMs have been go through the processing, reducing the noise of the DIM and filtering. Also apply the 3x3 medium to smooth the imagery and the priority flood algorithm to use. So basically the concept, I use it to detect the bit depression in this paper. So the phi in the level set equation, we consider 1 if the elevation of the Z it's greater by the plane intersect surface. I'd consider and the elevation it will be less than elevation of the XY if the elevation is less than of the point of the elevation of the point Z. So basically this concept, it's transfer the D or the image, the DIM to binary image by 0 and 1. The value is just 0 and 1. The second concept, the localized tree contours. So this is a concept it's used to describe the relation between topographic adjusted contour. So this concept, it's a 3 knot, the root knot and the internal knot and the terminal knot. And this concept, the depression, it's the depression of the bits. It's like a tree from the bottom to the up. So and for example, here in the graph, so A and C and F, it's considered the seed control, the seed contour, and P and C and E and D, there are not the seed contour. So the concept of the localized tree control, I use it just to highlight or to depict the complexity of the mining or the topography and the flood plain. So this is a graph we can imagine. This is the flood plain and how the open pit mine it changed the landscape. So using this concept, it can be detected the depression of the flood depression of the flood plain. So this is the study area, the pre-processing. So I divide the study area to reaches and the cross section. I divided the 6 reaches, A and B and C and D and E and F, and the cross section from the Lake Morphe to the state boundary, to the state boundary. So I divided approximately each reach is 10 kilometers. The first result of the level set method. So here the flood plain for the level set method 2004, and after in 2018 and 2018. So the method it's captured all the mining bits in or near the flood plain. So before the event, there was a 10 levels depression hierarchy in the flood plain. Also, after the flood plain, it's jumped to the 14 levels detect in the basin and 10 in the flood plain. And here example for the level set. Here image for the DN, and here for the after applying the level set method. So we can see the level set method, it's captured all the depression or the mining of the open pit depressions. And after the flood event, we can see this pits, it's captured by the river, and the level of the level or the depression level increases from level 1 to level 3. Or we can, or other words, it's increases from simple depression to more complicated depression. So I here example for the localized tree contour, localized tree contour. So different image, this image outside the flood plain. So we can see how the complexity of the depression of the nested hierarchical structure have been captured. So it's this graph is just illustrated how depressions inside depression, simple depression A, and how all of them becomes more complexity depressions, depression A. So for example, here simple depression A and B and C, and all of them become in more complex depressions. So this shows the spatial variation of this of the size and the size of the pits, which constitute the mining activity. The bathymetric change of the mining pits. So the size of the pits have been changed. More than 80% of the pits have been increased after the flood. The most increase in reach was in reach E and F. The number of the depression increased from 75,142 and from 17,112. Also, the depression levels or the depression hierarchy have been increased, especially in this reach A and F. It's an increase from level 1 and 2 to 3. It jumped to level 4, and in F it's an increase of level 1, 2, 3, 4, 7, 8, and 9. So in 2004, the LSM or level set method estimated 269 indicated depression, which can equate approximately 347,000 kilometers of the water. After the flood event, or in 2018, the level set method estimate a 347 indirect depression, which equate to the 498,000 kilometers of the water. So reach E and F, it had the most largest increase in the numbers, also in the levels. So the biothermal change in the flood plain resulted change in the donation process, affecting the water level, which also influenced the biochemical process according to the flood plain. And here the temporary variation in the area, in the pits area. We can see this is in reach D. This is 2014 and before the flood in 2018. After the flood, we can see the increase and the change of the sum of the pits. So before the event of 2016, the area of the total depression in the reach D and E and F, it was approximately 130 kilometers square. After the event, the flood event increased to 236 kilometers. The biggest difference was in reach F. It's more than 60 kilometers square depression area after the flood, where the smallest change were in the reach D. The level of the depression in the river floodplain before, it was just 1, 2, 3 depression hierarchy or depression levels. After the flood, it jumped to 10 levels inside the floodplain. Also, the river reach F has the most complexity part in the depression elevation. It's contain all the depression elevation in river reach F. The conclusion: the flood has in effect the river pit and the shape of the mining pit. The bare area and the pits made the landscape more vulnerable to the change during the flood. There has been an increase in the area of the pit between 2014 and 2018, which indicated that the flood water could have more water in the open pits. The second paper, it's discuss the channel dynamic and the geomorphological characteristic of the Amite River, Louisiana. So studying the long-term geomorphology of the river, it's helped us to understand the behavior of the system and the channel. So most of the work indicate the fluvial geomorphology have been focused on the before and after the flood event, or before after intervention modifications. The study have been investigated the impact of the mining on the channel, and this study can be classified as the three approaches: empirical, mathematical approach, or both. Devised of the morphodynamic problem associated with the sand and gravel mining operation, which are the river bed degradation, the channel instability, and the channel overload. There are many challenging in the mining, in the flood plain associated with the mining activity. So the objective of this paper, it's expected to be more channel instability in disturbed reaches rather than undisturbed reaches. And the aim is investigate how the land use and land cover change affect the channel instability by identifying the relation between the flood plain cover and the channel change. Also to bring comprehensive morphological analysis of the morphological change of the Amite River from 1998 to 2019 using the Morphological Indices, River Network Change Index, and the later mobility index and the channel mobility index. And here the flow chart for my methodology basically use three indices: the river change index RNCI, and the later mobility index LMI, and the channel mobility index CMI. And I use the global Moran to test it to determine the spatial relation between the land cover change and the channel change, and Pearson correlation to determine the correlation between the correlation between the land cover and channel change. So the morphological indices, the first one is the river network change index. It's so basically this index is used to subtract the sedimentation area from the erosion area, divided by the length of a cross section and divided by the year between the beginning and the end of the channel change. The second index is later mobility index. It's divided the channel active channel area on the previous active channel area multiplied by 100. And the third one is the channel mobility index. It's added the new channel, added the abundant channel divided by previous channel. And here, so the channel was divided to 54 cross section. And the global Moran autocorrelation, it have been used, and also the Pearson correlation coefficient. So the results, so here it's reject the null hypothesis, meaning there is a definitely relation between the river instability and the land cover change. So the global Moran, it have been more than 5. And with the significant p-value. And here the river change between the time period 1998-2004, from 2004 to 2015, and from 2015 and 2019. And here it just basically graph showing this is the in mining area, and here's the river of mining area. The blue, it's the river, and the orange is the sand part, and light blue, it's the mining pond. And here the result of the Pearson correlation coefficient. So there is the Pearson correlation coefficient, it have been by a channel change on the bit size and the sand part and the per area. It have been on the cross section scales, which is 54 cross section. The p-value was significant in 2015 and 2019 and 1998, but in 2014 it's not that significant. And here the result for the 2D Kell erosion activity of the Amite River. So here the map of the active channel. 2014, 2015, and 2015, 2017. It have been the biggest erosion. Sorry, it's erosion in hectares was in 2014, 2015, also in 2017 and 2019. And here just the change of the mining activity have been concentrating in this part of the river. So here the reaches A, B, C, D, E, F. So the highest erosion rate was found in the period to 2014, 2015 in reach P and C. We can see the river have been changed. The unchanged area were in reach D. So reach D and reach E, there's no any change area in these reaches. And the height accretion were found in 2015 and 2019 in reach P, reach P and C, reach P and C. And here a plot of the cross section, the erosion, the unchain, the deposition of the cross section. So, and here the geomorphological indices of the river network change index, later mobility index, and the channel mobility index. So the river network change index, the domain process was mostly was the erosion, except in 2015, 2017, it was the sedimentation. Also the change, the later mobility index have been high increase in channel mobility between 2015 and 2017. It's a change which indicate the flood event it had been in this period. The active channel area has be reduced by the later migration, and the river channel has become more dynamic in 2014 as the later mobility index increased from 78 to 140. From 2014 to 2017, it had been more dynamic later mobility index. The great city change was to be 2015 and 17, and the rich P and C show the greatest mobility and the change of over the time, while the river instability in the time period of the later mobility index. And here the all reaches for the all river for the river network change index, and for the later mobility index and the channel mobility index in the time period. So conclusion of further work. So specific to the study area, so the level 6 method has been able to detect the topographic and to detect and extract the characterizing the surface depression or the open pit mining and the geomorphological topographic property. Reach F has the complex depression level or hierarchy. The level increase in the Amite River from 9 elevation to the 14 levels, from 3 elevation to 14 levels. Also, there is a strong positive correlation between land cover and land use and channel change. And the highest erosion was found between 2004 and 2015 and reached P and C, which is associated with the mining, because the mining activity is concentrated in these reaches, with the 53 hectare and 36 hectare of land eroded just in 11 years. The highest channel change were in reach P and C, which associate with the intensity of historical mining. And the higher rate of the channel stability was found in the P and C because the mining activity. The limitation of the study area, it's can't prove and disprove that a later of the channel associate only with the land cover and land use change, and also the further analysis of the data resolution and the water level, and the further work. The third paper, I will discuss my dissertation as I was studying the likelihood of stream permeability using the logistic regression analysis. And this is my reference. And special thanks to my community member.
Any questions? Any from anyone in the room? Okay, how about online? Anybody have any questions?
I have a question.
Go, Tim.
Hello there.
Hello.
Hi, Miriam. I really enjoyed your presentation. The slides were really excellent. Good job on those.
Thank you.
Yeah, I have a question. So we got this open pit. First, let me just get this clear. We have the open pit minings, and where they are, when a flood comes through, it's going to affect the river system, changing it from its old course to a more meandering course from what I've seen. And there's a lot more dynamics, a lot more change. Now, what about afterwards? When these changes take place and the river, let's say, has moved to a more meandering state, or historically has those open pit mines migrated with those river system, let's say, migrated south, or did they move north? What's the response, I guess, what I'm asking of where the open pit mines are located, let's say, post-storm? Is there any consistency you see in how they're moving, where those mining activities are taking place?
So the mining, so the open pit, so this is illustrate the open pit. So from 1979 to 2019, some of them exist, some of them exist and fill with the water until now. So after the flood event, so the river have been captured the pits, like here after some of the bits. So this is, for example, before the flood event, before the
Right.
2016. So some of them have been captured, and it changed in terms of the shape, and some of them it just the level, because the level sits with its concept. So when it's detect the shape, so the shape it's detect based on the water level. So this here the graphics. So for example, this is the bits, okay, and this the water. So when the water low, so that's what's been detected. And when the water increase, this what been detected. And when water more increase, that would be the shape. So the shape of the bit, it should change based on the water level.
Yeah, but I guess my question is about what's the human response in terms of where the pits are located, like afterwards? If you go back in history, are they continuing to move out of these areas or continuing to stay in the same areas in terms of production?
So this is image. It's just for the floodplain.
Yeah.
I have some image, but it's kind of messy. I think it's outside the floodplain, but I didn't put outside of the. For example, I have some of the map here. This one, it's outside the floodplain.
Okay.
So the mining is just not concentrating on the emitter floodplain. It's expand also outside of the floodplain.
And it's more likely to do that, you're saying, post-event, if these things become, I guess, conjoined of these levels, or these pits conjoined. So they're starting to move just on the edge of the floodplain, outside the floodplain. Is that correct?
Yes, the mining activity, it's the floodplain also on the outside the floodplain, but the result here I just show the floodplain, just the floodplain, but there is some image outside the floodplain.
Gotcha.
Yeah, there is many of them. This image it's outside the floodplain. This one, and this is the floodplain. Sorry, I didn't include outside the floodplain, but it had been detected over all basin for the pits.
Yeah, thank you. I enjoyed your presentation very much. Thank you for that.
Thank you, Professor Faye.
Any other questions for Maram? So I'm checking through the online people. Any other questions from anyone here?
I have a question.
Katie has a question.
I'll just come up here since it'll be harder to hear me. Hi, Maram.
Hello.
In your second presentation, you mentioned that the second part of the second question, that you had the largest change in mobility between that 2015 to 2017 time period, and it was likely related potentially to the flood, the 2016 flood. And I'm wondering, during the other time periods where you do have changes in mobility, the mobility index, but maybe not quite as large, is that due to flooding as well? Did you look at other storm events? What else might change the, I guess, mobility index of the river?
So the major event in my study area, my time series in my study area, which are from 1998 to 2019, it's what 2016. The 2016 that was a major flood event, and that's. But there is also, I think, 2015. I think the flood, but it's not affected the Amite River. I think it's Katrina flood. But it's not affected. The most one, the Amite River affected, it was in 2016 flood event.
Right, okay, so, but you mentioned that you saw the largest change in mobility in that time. So I'm just wondering, when you see change in the mobility index over the other time periods that you explored, so if you go to that slide.
Let's see what you're talking about here.
Yeah, that one.
Okay.
So, right, you have that 140% for the 2015 to 2017, and then you have these other changes, maybe, 2017 to 2019. I'm just wondering what else might change that lateral mobility index besides flooding, if there's anything, or is it always, driven by flooding?
Well, this is the only explanation. I think I come up with the 2000 because the 2016 have been a flood. It happened in this time period, 2015, 2017. But I think you bring a point for 2017 and 2019. Also, there is an increase, but definitely there is another mobility, but my research is just focusing on the mining and the flood event as the driver of the regional instability.
Okay, so
But
like
I will
mining potentially.
Yeah, I will look up for the further to explain it.
Great, thank you.
You're welcome.
Anyone else?
I can ask a question. You mentioned management implications. Do you want to discuss any more about that?
Management practice for the floodplain. What do you mean?
Yeah, how do your findings influence or affect best management practices and decisions?
So the management for the mining activity, regarding the mining activity, right?
Yeah, that for sure.
Yeah. So it will be the dissertation will be the best practice for the river management and maybe for example for the region where is more vulnerable to the flood event, for example, which is considered in some regions. So that will be and also it's more vulnerable to the flood events. So that's one could be, and also let me see, the European. Yes, I think that's it.
Okay, thank you.
You're welcome.
Okay, well, thank you very much, Maram. And for everybody else, please make sure to get your speaker evaluation forms to Josh. And thank you. Good job.
Thank you.